Yes. Okay. Almost ready. Okay, before I start the other part, in case you have any question about that response matrix approach, so basically the idea is very simple, but maybe I did not give you very definite structure to it. Suppose these are the pumping values at different locations, okay, and these are the unit responses of pumping, or response of actually hydraulic head to pumping. So basically it says if you know the unit response for location 1 1, I am just differentiating between P1, P2, P3, P4, P5, and where you are monitoring is actually 1 1, 1 2, maybe 1 3, 1 4. So you should be able to get these values from this response matrix. So these represents nothing but unit responses of the hydraulic head to any excitation, any stress, and stress in the nature of pumping. Okay, I can also replace this by not hydraulic head but concentration also. It might be or concentrations at different monitoring locations. Again, is H may be C11, C12, C13, and I can do the same thing. Okay, so I can use the response matrix to actually find out what will be the response of a unit amount of pumping. And then I multiply by the actual amount of pumping, the P1, P2, P3, these are the actual amounts of pumping. So it's like a matrix multiplication. This one into this one will give you these values. Okay, if you know so this is known, and this of course you have specified. This is known. This is what you have found out. You should be able to get this. So again, if you have another time period, so it will go over here. So it is, so that is what it is. So you actually, I should not say that. So this is for the response of H11 to the pumpings P1, P2, P3, P4, P5 is given by, if you multiply this by this A1, B1, C1, D1, so like this, and then you can actually say so this is the summation of the effect of this pumping P1, then P2, P3, P4, P5 on H1 will be given by this equation. So that means like say P1 into A1 plus P2 into A2 plus P3 into A3 plus whatever is equal to H11. Okay. Similarly, I can have the effect of pumping on H2 that is given by another set over here. Okay, another set one is given by this one. Maybe let's say A is to A1. Maybe I don't know. Let's say A, capital B, capital C. These are the influence coefficient. Maybe that's not very nice, but so this is different from this. So that will, if you multiply this by this, it will give you maybe H12. That's at location 2. Okay, and then if you have not one time period but multiple time periods, then of course you can actually lag this by, so this everything will lag by one time period. So this is again A1, B1, C1, D1, F1, so something, and A, B, C, D. So okay, so and then maybe this is the first period. In the first time period, the pumping is this one. The second time period, maybe it is another one. So we double dashed P1, double dashed P2, double dashed P3, double dashed P4, double dashed P5. So something like that. You multiply by this one. Okay, second time period. Okay, so this will be for the first time period. For the second time period, so you are just lagging it over here and you get these values. Or if you find the response of the concentration to any pumping or excitation, that is given by C. So then this of course will represent the unit response of concentration to unit amount of pumping in these locations. Okay, is that okay? I mean, this at least give you some idea. Any question? Anything you did not understand? No. Okay, so I mean, if you read Gorlick's book, but it is convolution. Basically, it's a convolution principle, and you can write it in summation form, this and that, and all kinds of things. But the idea comes from the instantaneous unit hydrograph theory. So where it is a linear system, and if you have rainfall, different rainfalls, a storm has got different rainfalls. So what is the effect on the runoff will be given by something like this. Okay, so that's the singular idea. So that means in first time period, this is the pumping, second time this is the pumping, third time period is something. So you lag this by this like this. So this gives the effect of this pumping in the first location on H1. This gives the effect of pumping in the second location on H1. This gives the effect of pumping on the pumping in the third location P3 on H1. So this is what H11, whatever you call it, whatever. So I'm just trying to differentiate maybe this pumping location 1, 2, 3, 4, 5 or something, and then the monitoring location as 1, 1, 1, 2, 1, 3 or something like that. So this just differentiate, they're not the same locations, okay, nothing else. So that should be, at least you should get the idea from where it is down. So because we have to multiply this by this to get this, then they multiply this by this to get, sorry, yes. So this one for the first one, then second one you have to multiply this one by this one to get this, and maybe another one if you have another. So for H3 you have another similar responses, that is for H3 at location 1, 3. So that will be another matrix over here, okay. So for H1 these are the responses for H11, for H12 these are the responses, for H13 there's another responses. You have, it goes like this, okay, depends on how many locations of monitoring you have. So is that clear or it's more confusing? No comments. So basically you are saying this is my pumping matrix and this is my init response matrix, and which you give the effect is given by this, okay. So what you have said, this is the init response matrix, and here you have the head or maybe concentration, whatever you are. It's init response matrix is for maybe head or maybe for concentration. So you will get this. So this is to be calculated, this is to be computed, this is to be actually input over here. You have to calculate this. Of course, this will be a part that you will get this init responses. So you will get these values, and for any given pumping P1, P2, P3, P4, P5, you get this. Next time period you have maybe P11, P12, P13, P14, or P15 or something. Or I can put a time also over here, time period equal to 1, 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 and maybe this is P1 at time period 2, this is P2 at time period 2, this is P3 at time period 2, P4 at time period 2, P5 at time period 2. Okay, so you'll get this, and this goes on depending on how many you have. Okay. For response at H1, the location, maybe first location of monitoring, you have 1. Second location of monitoring is this one. This first monitoring location where you are measuring the concentration or the heads. First monitoring location, you have these influence coefficients. For second one, you have influence coefficient. Third one, you have influence coefficient. So once you have, that is for unit pumping. So then you multiply by the actual magnitude of the pumping and then add the effect, because all these pumpings will affect the maybe concentration or head at this point. So you have to take the effect of all. Okay, for that time period. Second one, you have to lag it. So this will be the effect of this plus this. Okay. Try. It's not difficult, but you have to think about it a bit. So that is what it is. Let me see. Now, before I go to maybe some other algorithms, one which, so we have discussed GA, that is genetic algorithm. SA, let me see if I have this. Somehow I forget which one is my G, no? Yes. this now simultaneously, let's just first give you the idea of what it does. So it uses some principle of thermodynamics actually, but this, you don't have to bother about the thermodynamics part of it. So what happens is that if you have metal like this, no, so the metal surface very rough, or crinkled and all these things. So if you hit the metal, so it's a metal surface. Okay, so you hit the metal, what happens that some of the crystals get enlarged, or some effect happens. It's like in metallurgy. So instead of this, you get start getting something like this. Okay, slightly more smooth. It becomes smooth. Okay, so if you hit that metal, so from here you'll get this, and probably if you are lucky and if you are doing it properly, ultimately you might get a surface like this. Okay. So basically you are expanding it. So basically it becomes like this, and then from here it becomes like this. So if you have metal, by hitting it, you will get a surface like this, and then if you have some well behaved surface like this, easier to find the optimum solution. That is the what. If this is your response surface, that means that your objective function for any problem that can be represented many times like a surface. Okay. And if the surface is very much undulating or crinkled like this and all kinds of things, so probably it is very difficult to find the optimal solution. But then you can use some analogy with thermodynamics and metallurgy by saying if I heat up this surface, then actually you can expand and and maybe add some energy or something like that, and you can make it like this and make it like this. So that is the whole idea. But it has nothing to do with the thermodynamics except that it uses this kind of similar mathematical principle. Okay, that's what it is. So and then what happens is that you have a problem where you think maybe it is difficult to find a global optimal solution like this, so many peaks and other things. So if you can actually make it smoother and smoother, so probably it increase the chances of getting an optimal solution because you're expanding it. So maybe you start with okay, here's the problem. You start with the given temperature. Okay, start the problem with some temperature. So that's the kind of mathematical parameter, and then try to find the solution or optimal solution. And then maybe you start from here or here, and you maybe improve a bit. Then you say you're stuck or something or not going anywhere. Then you increase the temperature. Okay, and by increasing the temperature, that is another parameter of optimization. So don't bother too much about it. Then chances are that you'll ultimately get, by doing that in steps, that is actually T equal to T plus delta T or something like that. Delta T is the increase in temperature. So you can actually make this surface into some surface like this, where it will be easy to find the solution which is optimum. Okay, so that's the whole idea. The only thing you have to be careful is what temperature you are starting from, T, whether that makes sense or not, and that is difficult to determine. Okay, and you might have to go through some trial and error. And the second thing is that what is the temperature steps of temperature by which you want to increase. Generally what you do is try to, because we are not getting an optimal solution initially, it's just arbitrary starting point, we make this delta T large, so try to make it as maybe expanded as possible. And then if you think that it is kind of converging to but you can look at the solution, maybe it is here somewhere and here or something like this, but then maybe it is coming something like this. So here you make the delta T smaller. Okay, make the increase in temperature smaller and smaller, so it becomes finer. Okay, so that is why. And then because you are coming close to the optimal solution, and then chances are that you will be able to find out what you call is a global optimal solution. Do you have to bother about So this is another algorithm. You can use this as a black box, but you cannot really use it as a black box because you have to understand a bit about what it is about. Okay, so if you don't have any idea what is this temperature increase or what is the initial temperature, maybe you will not be able to solve it. Okay, so that is one of the issues. And problem becomes because you don't know what is the starting temperature is the right one, and what is the rate of increase of temperature which is the right one. Okay, so but you can try, and I have seen my experience is that it is the solutions are very much sensitive to this T and delta T. Sorry. And if your T and delta T choice is not right, it might take a long time to get a solution, even if close to the optimal solution. And therefore, you have to use some trial and error values of t and delta t and see which one works. Sometimes some solutions took some few days of computer time, and sometimes the right choice of t and delta t took only few hours. Okay, it's possible. Okay, and I don't know what is the best answer because very difficult. There's some thumb rules given in some of these programs, but the thumb rules sometimes don't work. Okay, but how to choose t? So to improve this, what we sometimes now you're using ASA, which is adaptive simulated annealing. Okay. Oh, it is going beyond this. Anyway, so adaptive simulated annealing. The difference between simulated annealing and adaptive simulated annealing is this. Like many other models, adaptive means you generally the estimation of the parameter, which is the parameter of optimization, like the starting temperature, rate of increase of temperature, is determined by the program itself, depending on the data you have given. So it is kind of it is the responsibility of the program to find out what is the best one. It may not work most of the times, but it is generally quite efficient. Okay, so it is not up to you to give this parameter values, but this for they look at the program will look at the data structure and find out what is the best value of these parameters. Okay, and that helps a lot. Okay, so adaptive simulated annealing is very useful from that point of view. And we have some papers where we kind of compared the solutions of GA, a genetic algorithm, and this simulated annealing and ASA. Generally, my experience is that ASA is certainly more efficient in arriving at the global optimal solution compared to GA. Okay, and certainly it is much more efficient than SA, because SA, if you are lucky, you might get a solution which is quite efficient and fast. If you are unlucky, you might be just searching everywhere and not really converging to a solution. Okay, so therefore that uncertainty is partially covered if you use ASA. That's very important to understand. And nowadays we work with ASA because I think it is, and also this initially the solutions are actually generated by randomly generated, just like it is kind of similar in many ways to the GA, because initial solutions are randomly selected, all kind of things, but then again there are some random elements. So it is also in a way a bit of random search method, but not really. There's a lot of other things in addition to the random search. Okay, so therefore it is much more efficient than, of course, random search most of the times will not work. But one thing with random search is that its chances of getting a solution is at least there. You get some solution which may be feasible but not optimal. But with the classical optimization technique, where it looks for this gradient search method, you may not be able to even find this feasible solution. If it is a very complicated problem, it's very non-linear, you might not be able to start from a solution which is feasible. You have to search for that solution which is feasible solution that satisfies all the constraints. Especially if you have many constraints, many nonlinear constraints, you might not get a starting point which is feasible. And if you cannot find a feasible solution, then chances of getting any solution is very less. Okay, with this random search method, is almost sure you will get some solutions. It may not be optimal all the time, but chances are also good that you will get an optimal solution. Okay, so because when you go to nonlinear optimization, things becomes very complicated. Another thing I don't know, I think many of you have used MATLAB, no? Some of you MATLAB? Some of you familiar with MATLAB? Mathematical something. Yeah, so nowadays MATLAB has got lots of these programs. I think it might also have this SA or GA certainly. They have a GA version. I'm not sure if that is a good version or not. The one developed at IIT Kanpur, I think, is slightly more efficient, because they are the ones who are like in the forefront, at least in developing the software. But MATLAB has got most of this. So if you are using MATLAB, so that's the mathematical package, some programming packages, the statistical packages, optimization packages. Then you will also get this artificial neural networks and all kinds of things, that so-called AI techniques. I'll discuss a bit about that, so that is useful. So if you're interested, I'm not 100% sure about SA, but GA is certainly there. Okay, in MATLAB, and that's is not of course MATLAB is not a public domain software. Generally, but many of the universities do have MATLAB because it's used by the students. It's a very common use software. Okay. So having said that, and let me just give you an example. I have not gone into monitoring network design, but I will give you some at least some results. At least it gives you some idea about what it is about. I hope there is a this is the transport equation. You know this, so including the also the reactive term is included over here. Whether you include or not, of course, that's another thing. So and this gives you kind of the steps, okay, in the simultaneity. Okay, of course, first initialize the candidate solutions. It may be randomly selected, maybe as part of the algorithm, so you will select it randomly. So first initialize a candidate solution and estimate the initial temperature. Initial temperature is the one I was talking about, that sometimes you are not sure exactly how to and what type of temperature is given, but if you have some experience, probably you'll get. Otherwise, just go for some kind of guidelines will be given in the programs. Most of the programs in the comment section at the beginning, they tell you, what type of temperature you can, initial temperature you can choose, and what type of delta T you can choose, that is change in temperature. Okay, so then after that, randomize solutions according to current temperature. So the temperature will determine the random solutions that are chosen. Somehow it is function of that, and run the transport model with generated value candidate solutions. Let me just check one more thing. Yeah, this is more or less the algorithm. Now, as I said, of course, I am talking in terms of the linked simulation optimization. As I said, all this is also an evolutionary algorithm, not a classical optimization technique. Linked simulation optimization model, that is what we are talking about. So obviously, when you have these are very, very useful. As I said, both GA and SA are very useful. It's easy to actually link the model, and that is what it is. So first you initialize the candidate solutions and estimate the initial temperature. It is a rule of thumb, or somehow you estimate it. Then randomize the solution according to the current temperature, because that is a function. Somehow those numbers are generated will be a function of the temperature you have specified, the initial temperature. Then of course, because it's a linked simulation optimization model, so run the transport model with generated values of candidate solutions. That means random solutions are actually generated over here. That is a function of the temperature, initial temperature. So obviously that will affect the values that are generated. Then use those. Maybe I don't know which objective function was used here. Let me just see. Yeah, if I can. I have not discussed too much of this source identification, but anyway, but I think that's not that important. If I had, probably it will be slightly easier, but then let me just give you the algorithm first, and then we'll do all these things afterwards. So because the linked simulation optimization model, and of course I'll just say that the aim of the model is to identify unknown groundwater pollution sources. So that's the aim. How do you do it? So you have an area, you have some values. So let's say these are the monitoring data or observed data of, or maybe concentration measurements. You have some few of them, and you don't know really what is source, because you don't know where this contamination is coming from. You don't know what is the source. You don't know. So by source, again, I'll probably discuss it afterwards. Source, by this you mean magnitude, timing. That is, maybe I should say timing of start and duration. So when you talk about source, these are all important. So that means you are not only looking at the magnitude, what is the source, what is the magnitude, then how long the source was active, for 1 year, half a year, 2 years, 5 years. So that is very important, and it can vary within that time period also. So duration is very important. Timing is a starting point. maybe you are thinking you are in 2010 or something, and maybe this has started in 2013. Okay, so you should know when it started. So that is another thing to find out, whether it's 2010, 11, or even before. So timing, the duration, total duration, and of course magnitude. Unless you know the magnitude of the flux, maybe kg per second or something, milligrams per second or something, that is the magnitude of the flux. Flux, that's the per unit time, and mass, that is the mass flux. So therefore magnitude is in terms of kg or milligram or grams, whatever it can be. Okay. So what you have is, in this problem, you have the measured concentration at this point, measured concentration at this point, measured concentration, few of them, maybe for few years, and you don't know anything about where the source is, where it's coming from. So you want to, maybe only thing you know that there is possibility that it may source might be here or here or here or here, here, something like that. So some information about potential sources are there. So potential source location and potential sources are there. So you don't know whether really any one of them is actual source, or it's just that you are thinking is a source. So but it is better to include as many as possible without increasing the computation burden too much. So maybe you think maybe there's a factory there. They have dumped something in the night or something, or clandestinely, or maybe there's a septic tank that is leaking, or all kinds of things. You might have some information that these are the possible sources. Is possible, because otherwise every node becomes a possible source. Theoretically that is okay, but that means you are trying to find out out of thousands which is the source. Magnitude, location, duration, that becomes almost intractable problem. Okay. So it's most of the times you need some information about maybe some locations where it is possible, and so that you don't have to go for wild search for those. Okay. So let's say the problem becomes if there are multiple sources and they overlap. So from this source maybe the plume will look like this. Okay. The concentration plume looks like this from this source. It is spreading with time, and suppose these also is active and these also active, and from this source it is like this. Spreading, and what you might have some measurement of concentration at this point and this point. Okay, which shows some concentrations. And then maybe next year also you also have maybe this location you have some concentration, because the plume might have actually gone this far. You will have some values here or here somewhere else. Okay. This most problematic case sorry, because the plumes are overlapping. So when they overlap, it is very difficult to say it's one source or two source or three source, because the effect is like a mixture of the effect. So you don't know it's actually coming from one source, maybe three source or one source. And also you are not only talking about location wise, timing. It may be the same source but different timings, different values, and that might be also another problem. So it might be you see some concentration because it is coming from multiple sources, more than one source. That's why seeing this, or because it's coming from even a single source but different releases at different times, and which is giving similar effects. Okay. And the question is how to find out which is the correct one. Okay. And I'm looking at both magnitude, timing, and duration. Only thing I kind of have some idea about what are the potential locations, and then I said okay, maybe these are the possible locations. That is the only thing. So I'll discuss this afterwards also, some examples. I'll just wanted to say what is objective function is. The objective function in this case will be, so that means you have concentration observed at this point. Okay, C observed at this location, C observed at this location, and it may be for 1 or 2 time period, or 3 or 4 time periods, and 3 or 4 time periods over here. Generally in these cases where it is first detected, there is very little data about the water quality, and therefore that is one of the more important challenges. Okay, because generally when it's first detected some pollution in the aquifer, very few data is there, because nobody has monitored the water quality. Okay, so that is one of the things. So what is the objective function? I can say that maybe let's minimize this. Okay, C, I'll just use this one so there's no C estimated. Okay, sorry, C estimated and observed at time k maybe minus C observed at location IUB at time k. square summation over all time periods. Okay. So, and all locations IOB, that is the location, IOB is 1 to maybe n or something like that, and time period is actually k equal to 1 to nk or something. So, you have 10 time periods, you have this data. So, nk will be 10, and you have maybe 5 locations where you are actually observing these values or measuring these values. IOB is equal to, or what is that? No, this NOB, sorry, this limit is NOB. So, IOB is the variable, and then NOB is equal to maybe 5. That means 5 monitoring locations. Got it? So, 5 monitoring locations, NOB equals 5, 10 time periods, nk equal to 10. So, this of course k is a variable which goes from 1 to nk, and IOB goes from 1 to IOB equal to 1 to NOB. Okay, fine. So, what I am trying to do is to now minimize this difference between C estimated, that is estimated by. So, this will come from your simulation model. Okay, this is estimation means simulation model that you have, and your C observed, which is known. These values are known. Okay, these are known. Correct. That means what it says is that you try to minimize the difference, but between what value of concentration has been simulated at this point. At this point, you have simulated some values, and you have some observation. So, you try to minimize the difference between these two, or try to make sure as close as possible. They are as close as possible. So, your objective is to minimize the difference between this. Again, I am using a square, so that plus minus values do not. This is greater than this will plus, this smaller than this will minus. So, you sum it up, it might become 0, but it does not mean actually there is lots of difference. Okay. So, see, therefore, you can use, as I said, absolute value also. Fine. Now, the question is, where is the simulation model coming from? So, these are coming from simulation model. So, that means I have to minimize this, and what is the decision variable in this case? Actual decision variable. The decision variable is source. Okay. Maybe they have 3 sources at time k or time t, whatever it is, S1 t equal to 1, 2, maybe something 3, 4, 5, whatever you want to assume. S2 another source, S3 another source for all time periods, Okay. So, these are, you want to find out what are these values. Okay. So, you have this study area, and this is one source is S1, and another location S2, another S3, another you might have S4. If it is not a source, it should come up with a value. This is, suppose S4 is not a source. You assume it is source, but it is not a source. Then your optimal solution should show, if it is correct, solution should show S equal to, so S4 is equal to 0. Okay. So, even if it is dummy, so what we call a dummy source, because we assume that it is possible, but actually it is not a source. So, it should actually, the optimal solution should show that it is 0, otherwise your model is not correct, your inference is not correct, and it is not showing. So, what you do is that we know these values, C observed for few values. Then we have a simulation model for flow and transport. You generally need both flow and transport models. That flow model at least has to be calibrated. In this case, flow model is calibrated and validated, otherwise not a model. It does not represent what is happening in the field. Now, I am not saying that for the transport model it is calibrated and validated, because you do not know the sources. You really do not know the sources. How can you validate it? How can I calibrate it? So, you cannot calibrate it, but you should know that at least the flow model is correct, because and so you cannot match what has been observed. The concentration has been observed in the field by just calibrating it, because you do not know the sources. So, how can you actually generate the source, the concentration values? That means you do not know the source. So, how do you know what will be the concentration at this location? you don't know. So, therefore, calibration will not be possible, but you should at least calibrate the flow model, okay. Because if you could calibrate that model, then you do not have to go for source identification, you know the sources. Okay. So, first I have a calibrated flow model, and also I implement the transport model, of course. So, it will use the flow model output, and maybe it will need the dispersion coefficient, all these things. It must be the best estimate you need, and also maybe the boundary conditions necessary, that you have to give the boundary condition for the transport model. Without that, it might not be acceptable. Okay. Then, if I want to minimize this, so this is the objective function. So, basically subject to the flow and transport model, simulation model. So, you cannot just say I will minimize this quantity, but that means because these C estimates should come from the simulation model. So, obviously, it comes from the simulation model which you have implemented. So, therefore, now the question, because you have to link this model, link this model, the flow and transport model, to the optimization model, because really the implicit constraint of this model is this simulation model. As I was describing in the morning, implicitly you have to satisfy the condition that the physical system is actually simulated properly. Okay, that is what it is. And then your decision variables will be this source 1, source 2, source 3. Maybe at different times it is different also, so at time 1, time 2, type 3. And when you actually solve the optimization model, so what is your candidate solution? So, it should come up with different values of S1 or S2 or S3. Okay, it should come up with different candidate solutions. So, S1, S2, S3, S4, S5 for time period 1, maybe S1, S2, S3 for time period 2, S1, S2, S3, S4 for time period 3. So, these are generating those candidate solutions, going back to the simulation model, and then find out if these are the sources. And because I know everything else, that I know the flow model that is when calibrated, I know the more or less the boundary condition, but I do not know the exactly sources, but I input these as sources as input or in input file, and then find out from the simulation model what is this estimated C for these source values. Okay. So, for this candidate solution, that means which is generated as a possible solution by the optimization model, I put that as input to the simulation model. So, what I get out of that is the concentration at different monitoring locations, and then I try to find out again what is the value of the objective function, which will give you the summation of the square of the differences between the estimated values which is coming from the simulation model and the observation values of the concentration. So, this is the difference between the estimate values of the concentration and these are known values or observed values of concentration. When this you have minimized this, that more or less you are getting the fit, and if that happens, there is chance that for which scenario you are getting this minimum value. So, for that scenario, what are the values of S1, S2, S3, S4, whatever it is, the sources that are the possible sources. So, that is the source identification model. Okay. You understand this? So, unknown here is the sources. What we have observed, some of this. So, of course, there are lot of complications. If you have only very few observation points or monitoring points, it becomes very erroneous. It's your estimates are not very correct. So, all kinds of things. But then that's more other challenges. So, what I am saying, this is my objective function, and it is subject to the simulation model, both flow and transport, and therefore, this is ideal case for a linked simulation optimization model. Okay, this is a linked simulation optimization model. So, that is what it is. And then what do? Maybe the algorithm that is used for solution is that I know this is my objective function, I know this is my constraint, which is the linked model. So, then how do you actually solve the problem? Use assay. What will be the job of assay? First, of course, it will you provide the initial temperature, maybe the time step for increasing the temperature, and then the optimization model of itself generates this candidate values of S1, S2, S3. So, all these candidate values, and goes to takes them to the simulation model, finds out what is the resulting observed value of concentration. Okay, sorry, resulting simulated value of the concentration. Sorry, what is and finds out what is the resulting simulated or estimated values of this concentration, and sees what is the difference between this and the observed values or measured values, actual what is measured in the field, and then goes to the next iteration and see whether it can minimize or further minimize this objective function value. Ideally, it should be 0, but probably it is never possible to have a 0 value, because if everything was fitting, they should be equal, it should be 0, but probably that never happens. So many other factors are there, but by every iteration is trying to maybe improve that objective function value. Once it is very small and you can have a stop, maybe stop searching further, then you know that probably those are the values for which you can actually assign, or these are the values you can assign as S1, S2, S3 or the sources, and you have solved the source identification model. Okay. As there are many other subtle points. I know this is something like a weighting function. Sometimes if you don't weight it, because this, if some of the concentration observed are very small and some are very big, so it might not give a very good efficient solution if you don't normalize it. Normalize it means maybe this difference should be divided by the actual observed values, so that is kind of, if your C observed is equal to 100 and another C observed is equal to 10. So, an error of 1 in 100 is nothing, error of 1 in 10 is actually something like 10%. Okay. So, therefore, we generally divide by this quantity, that C observed plus n is so that if C observed equal to 0, it does not become 0, n is a small number, so that it never becomes 0. So, 1 by 0 is of course indeterminate. To prevent that, we use addition of a small number over here, so that this never becomes 1 by 0. Okay. So, that is the whole idea. Okay. But it increases the efficiency of the model. So, this normalization, otherwise it will be kind of wrong kind of fitting that will be. So, here this is an example that we have of course use essay, and as I said, from this context now you will understand this of course. So, you start with this maybe initialize candidate solutions, which is like in this case maybe the possible values of the source, magnitudes, of course locations. So, in location 1 is S1, location 2 is S2, location 3 is S3, and for different time maybe S1 at t equal to 1, S1 at t equal to 2, S1 at t equal to 3, all these things. So, these are the candidate solutions, and this can be generated by randomization. There is, or that the randomization mechanism is already part of the algorithm. Then, because you have now generated the candidate solutions S1, S2, S3, we go back to the simulation model, find out if these are the sources, what will be your C estimates, that is what is comes out. And because now you know what is your C estimates, so therefore, you should be able to find out the calculate the objective function value over here, and then of course, you should check whether this solution is better than last times or not. Maybe there is improvement. If it is better, then you replace the latest solution is the best solution, then that will be the solution you keep with you and forget about the other solutions. If it is worse, then maybe keep the last solution and forget about the other solutions for the time being. Okay. That is again something like elitism that we are talking about GA. That means, if the solution has improved, take the improved solution. If you actually think the new solution is worse than the last one, keep the last solution. Okay. So, at least you have that minimum value of the objective function. Okay. And you can go on repeating this case. Is the solution better than this? Reached maximum tries. Now, stopping criteria is another very big issue, and those who will do some research with optimization, if when one of you do it, you should be very careful about the stopping criteria. Criterion or criteria, depending on singular or plural. So, as I said, you might generally these are maybe iterative techniques, number of iterations or generations. Very important. Number of iterations or generations are very important. And then question is that what do you stop? Suppose you see that your objective function, these are your objective function value, okay, and let us say you are minimizing, okay. That means, so it goes like this. It is possible. Then you don't know where to stop. You cannot stop here because maybe you can minimize more and less, and then again it goes like this. So generally, you should fix, one way is to fix that maybe for 100 or 1000 iterations there is not much change. So if you have a situation like this, you can more or less say that that you can stop here because you cannot improve it much. Okay, but not always. But I have also seen after 1000 iterations suddenly it becomes like this. Okay, here. So it does happen. You cannot prevent that, but then you have to be reasonable. So you cannot do maybe 100,000 iterations, probably too much for a problem. Sometimes it may be necessary. So stopping criteria may be given by the number of iterations, or you just visually look at the optimum solutions and see, or so-called optimum solutions, and see whether you are getting some kind of stable regime over here, and maybe it is safe to stop over here. Okay, you may not be able to. So that is one thing. That is true all for SA. That is it's true for GA. So I prefer this one, that I look at the solution and try to make an idea that whether it's really, I feel that it has stopped, reached some kind of equilibrium state where you probably will not be improving much. Okay, but sometimes I have seen, I thought it is, we have reached the best solution, but after few hundred or few maybe 1,000 iterations, suddenly just testing, we see that is again decreased like this. So maybe this is the one. So but there is no hard and fast rule. I cannot set the rules for this. So that is very important stopping criteria. Some people say, okay, number of iterations should not be, you limit maybe less than equal to 10,000. No matter what, is not a very good idea, but then that is the stopping criteria they use. It might not be very efficient, may not be very proper. Okay, so what stopping criteria you use also determine what type of solutions you are getting and whether you are getting an optimal solution. So here again is the maximum tries. Here of course we suppose you have put a number of limit on the number of iterations. So reach the maximum tries. That means how many times you are trying it. Maybe iterations are maybe 10,000. So maybe you should. If not, you continue. If yes, then decrease the temperature by. So this is what is the point. So what I am saying is that here it's slightly different. Here you are getting this. You think that you have reached an optimal solution over here. But maybe you can try, but by decreasing the temperature, by reducing the temperature. So by reducing the temperature, what you do, you make the search more sharp. Okay, so maybe you are in this area only, so you are sharpening more. You are searching more in a more efficient way in this area only. So therefore, that might give you a slightly better solution than what has been achieved before. Or you can say, I'll change the temperature only after so many iterations. Maybe after every 1,000 iterations. T or delta T may be changed. Okay, so here it of course determine temperature by specific. Yeah, so here T is changed. Okay, sometimes you also might change delta T, because as it comes closer to the optimal solution, or you think it is coming closer to the optimal solution, you might make delta T smaller and smaller. Okay, that is also possible. Sometimes that helps again. And then you might also put some kind of lower bound on the temperature. That is only true for this and so symmetric annealing case. You said, okay, I'll go, maybe I start with 50 degrees and then I'll only go to up to 10 degrees or something like that, not more, not less than that. If that is reached, I'll stop, no matter what. Maybe again it's a questionable criteria, but sometimes it works. And if that logic is satisfied, that this condition is satisfied, you stop and then you say, okay, I have got the optimal solution. And for the best optimal solution, that is for the best objective function, you find out what is S1, S2, S3, and that will give you the source, estimate of the source, okay, of the unknown source. So in the process, what you have done, you did not know where the pollution is coming from. You also had no idea what is the magnitude, when it started, and when actually it ended, so duration. But this will help you to find out what might be the sources. Not that always, there are lots of problems, maybe I can discuss a bit more. This non-uniqueness problem, because wrong combinations might give you the right answer and they might think that is the best answer, but that is not. So it's a wrong combination of sources. So that's called non-unique. A system, like I might have two sources over here and here, and they might give a breakthrough curve like this, or I might have another one far away and one very close. These two maybe, that might also give a breakthrough curve very close to this. Okay, I don't know whether this is correct or this is correct, and sometimes so that's non-unique. Okay, non-uniqueness is one of the biggest problems. And another problem is ill-posed. Ill-posed is that if you have only very few observation values, and you have maybe 3, 4 possible sources, and they might overlap. That starting time might be different, and only you have 3 or 4 or very few observation points. That data may not be adequate to even correctly identify. Okay, so that means your problem itself is ill-posed. So how to solve that issue? That is where the monitoring network comes into picture. You design a monitoring network, implement it, get some more data, make sure that design somehow helps you in a better estimate of the sources, and that will actually improve it. So, ill-posed nature of the problem can be dealt with. Non-uniqueness is much more difficult, because as I said, two different combinations might give you the similar results. So, therefore, you do not know which is better. So, that is one thing. Also, even not only space, maybe timing. So, maybe here this one and this one might give something, and this one and another source, maybe the different one timing is like over time, maybe this is the concentration, this is the concentration, this is the concentration, this concentration. Another might look like this or something like that. So, it is not a very good one. So, and this is smaller and bigger or something, some kind of combination which is same location, but different values at different times might also give you the same breakthrough curve, that is concentration versus time. Okay, this time versus concentration, and therefore, it is very difficult to differentiate whether this is better solution or that is better solution. So, that is ill-posed and non-unique solutions are one of the problems. But anyway, so I will discuss that a bit afterwards. But here, of course, as you can see, this is the flow equation, and I have already shown the transport equation, and the objective function is very similar. As I said, that is of course, this is the objective function. The weight, as I said, is normalized, sometimes make it more efficient, not always. We had some studies generally it is more efficient to use that. And also, and the interesting part is, suppose you do not know you have not got, and it is possible, I am not saying it is the best, it is always desirable, but you might not have calibrated your model, even flow model adequately. Okay, and then you do not know what is your hydraulic conductivity values exactly, or porosity values. So, you may treat those as unknown also. You might treat them as decision variable also, so that it will try to generate random values of those hydraulic conductivity, porosity, maybe all these things, and then also try to get a fit between what has been observed and what you simulate. So, by doing that, you might be not only able to estimate the source concentrations, but also some of the parameters or flow parameters. Okay. So, you can use that for simultaneous estimation of some of the flow parameters and also the unknown sources. But what my experience is, so we tried that, did not work very well, but it works well when you not only include the concentration values in the objective function, because you are trying to minimize the difference between measured concentrations and simulated concentrations, but also you add another objective function or a part of the objective function where you try to minimize the difference between the observed head or measured head and the simulated head, just like this one which is coming. And if you combine these two objective functions, then you might be able to do this simultaneous estimation of parameters, which is like the inverse problem, and also the sources. So, not that you have to always know what is the value of the parameters, this can be simultaneously estimated in some cases. Okay. But you should include hydraulic head in the objective function, that is very important, otherwise it does not work very well. Okay. So, this is an example, and we have so many other examples we will discuss of this assay application. And again, if you look at this, some of this, this table gives you some of the ideas. These are the study area, length is to what 2.1 kilometers, width of the study area is 1.5 kilometers, thickness 30, grid spacing is 30 meters. So, all this, and okay, I don't know, and yeah, these are a comparison of the ASA method. Of course, we are using adaptive simulated annealing in this case, which is much more efficient, and also GA. Okay, and you can see without going to the average part of it, and I think this is the the solid line is the GA. The solid line, as you can see, is the GA solutions, and this dashed line is the ASA solutions. And you can see the objective function value is much lower when you use ASA compared to when GA. That means actually it's much more efficient. Okay. So, you are getting a smaller value of the objective function because you are doing minimization. So, that is better when you are using ASA. So, that ASA is giving, you can see the objective function value is smaller, and for GA it is larger, as you can see over here. Objective is above this all the time. So, that tells you that maybe ASA, at least in this example problem, is much more efficient. And I'll also show you some of the results, which is I'll discuss some of these things afterwards also, and then some of the applications. This was more of a hypothetical study area, so not real study area, but because we wanted to again find out how it's working. So you can see, so the estimates by, so first one is by the actual value of the source, maybe like in location, first location source 1, actual value is the first one, this solid line which is in this one that you can see, first one. Then second one I think is the ASA, what is been estimated by ASA. Third one is what has been estimated by this GA. So it is very difficult to say which is better, but actually objective function wise, this shows, ASA shows better convergence and faster convergence. And here also you can see with GA probably you are getting much larger error compared to the error that you get using the ASA method. Here you can see they are very close, but GA value is quite different. So of course you can not only use this visual comparison, you also have some statistical comparison techniques. We have used those, and then of course generally ASA works better. This was source 2. This first one is by the actual value, second one is by ASA, third one is by what is been estimated by GA. And you can see of course they are comparable, but so this is very important. This is another solution that here average of GA based method. So of course we are going from one to another, second one you take the average of first two, then we will go to third one, you can take the average of 3 or something. So forget the average part, but what it says is that you can see average of the ASA which is the dashed one. Objective function is consistently smaller. For the number of iterations you can see this very soon it converges to a very small value, but in this case it takes a long time to converge to a small value which is near to 0. So from this point of view, ASA is also much more efficient. Okay, so that you can see, and these are again some other cases. These are some criteria. That is what I am saying, statistical criteria for comparing. Now you will not be able to actually find out whether it is working good or bad, or it does not work at all, unless you take a hypothetical situation. As I said last time, I think I said that if you take a study area where you do not know what the source is, but you have some observations, so whether what source you get, you will never know whether they are correct or not. You will never be able to say whether correct or not. Who says that is correct? It may not be, because we do not know the sources really, and it is very difficult to measure the sources. But what we do again, we try to take a hypothetical area where we assume first I know the sources S1 and S2 and S3, whatever it is, and then find out what will be the concentrations at these locations if these are the sources. Then use these as my measured values of concentrations and forget that I know the sources. Put these input values in the objective functions as the observed concentrations, and then try to find out what these values are, S1, S2, S3 are. Okay. So I am using these values in the objective function. From that I am trying to estimate S2, S1, S2, S3 the sources, and because I know for what S1, S2, S3 I have got this observation, so then I can compare. Are they saying 5 minutes or no? Okay. So because I know actually sources, what are the sources, so I can actually judge whether this method is working or not. Again the same thing, and these only for evaluation purpose. So don't confuse this with any other, because in actual field you will not know it, so you have to believe that what you are getting is okay. But you should test it by this method maybe first, saying that you assume a hypothetical system, then you generate the values or simulate the values of concentration measurements for given values of sources, then forget that you know the sources, then give the concentration measurement values which have been simulated by the simulation model, use them in the objective function, that is the C estimate minus C observed, and the C observed are the ones which is coming from the simulation model, and then of course then you solve the optimization model and see what is the C estimate or what is the S values you are getting, so that these minimize, these objective functions minimized, of course the summation and square, and then you try to see whether that compares to the actual values for which you had simulated these observations. The observations have been simulated for known values of this, and you try to find out whether you are getting those same values or not. Okay. That will tell you that is working, otherwise there is no way to tell. Okay. So people sometimes start jumping, say, oh you assume first you know, then you don't know, then you know, then you so it does not make sense, but actually it makes very much sense. There is nothing unscrupulous, nothing cheating. So it is because the optimization model does not know what the source is. I know, but that is only because I want to compare the solution and see whether it's matching with that. Okay. So when I'm solving the optimization model, it has got no idea what the sources are. Okay. It only knows what are the concentration values have been measured, and from that it is trying to find the inverse problem, solving the inverse problem and see what could be the sources. And if those sources are matching with the values that I assumed for getting those observations by simulation, then it's working. But as I said, we complicate the things by adding error terms to that actual simulated values and other things, and tell the optimization model that is not the actual values of the simulation model, but simulation C simulated plus some error terms which are randomly generated, and then tell the optimization model this is your C observation, and not the C which have been simulated. Okay, not the C simulated, but this plus some error terms, so that it's actually not getting the exact values. And if it works, then it replicates some of the things that happens in the field. Okay. So this is an application of essay. GA, of course, I could have done, as I said, we have done it with GA also, but I feel that the essay is slightly more this thing. But if anyone want to use it, especially, I have a feeling that link simulation model is almost inevitable with the power of computer that is today available. So link simulation optimization model can solve almost any problem, because no matter how complicated and sophisticated your numerical model is, linking is very easy, provided you use this SA or GA or some other evolutionary techniques. But if you want to use classical optimization, no, it will not work. Yeah, very difficult. Okay, almost impossible. Embedding technique, small systems works. The moment it becomes big, I think there are some papers. If you just search for it, they comment about the embedding technique. So generally, for any decent site, it will be very difficult to solve that, because it becomes too big. Because you have to use each and every finite difference equation at every node, or every finite element node or finite difference node. You have to use that as constraint. The constraint might become few thousand, and if you have a nonlinear optimization model with few thousand constraints, it's almost unsolvable. Okay, so that's what it is. But I'm confident that with link simulation optimization model, anything you can do, source identification, you can do any flow model, you can use transport model, heat transport model, heat transfer model, anything you can do, and then you can do the optimization. Okay. Anything else? No. Okay. Yeah. Suppose I assume 5 potential sources. Okay. And I know, or I suppose 2 of them are dummy. By dummy I mean it's not actually source.
So actually you are putting a maximum value.
Oh, okay. Oh, it's coming now.
Actually you are putting a maximum
Yes.
value, and you have identified some are dummy sources. But if the actual number of the sources is greater than the value which you have assumed.
Oh, if it is more than that, you cannot find. That's why you have to be careful in choosing the potential numbers, because see, you are defining the decision variables, and only it can say whether that decision variable is 0 or not. That is actually not a source, but you have assumed a source. But if that is not even a decision variable, how can it's out of the picture? It cannot. Yes, but then the solution to that, if you are not sure, assume more potential locations. But generally, what happens, of course, I can look at some of this, maybe observed, if there is some observed concentrations, so we can make some idea of where the potential sources might be. Not the actual sources, but at least the potential sources might be. Because I had looked at some sites, defense sites and nothing in Australia, and then so hydrogeologists were saying that they think this and that. I said, no, that's not possible. So because then say, how you are civil engineer, how do you know? You don't know anything. But I said, no, but I can understand what it is. So they think that civil engineers don't know anything about hydrogeology. But looking at it, you can make some guesses. But if you have only one monitoring point or something, so then there's no way. You might start with 1 or 2, but then if you have fair amount of 5, 6, 7, 8, where the plume has been captured, we have done also that kind of work. But I didn't cover it over here. That you look at the pattern of those plumes and whether you can separate it out. The biggest problem is that you don't know whether it's coming from 1 source, 2 sources, 3 sources, especially if they're close. Then we tried use kriging and some refinement, I think, just on the observed values, and to see whether you can separate the plumes out and say that whether it's coming from this source and second one is coming from this source. Okay, so some work has been done. I think he's not there. Om Prakash's student? No. My student, oh, he's not there, I think. Today he's not there. Anyway, so yeah, my student's PhD student. Yeah, I forgot his name. Anyway, so yeah, he did his PhD thesis, at least part of it was devoted to this. We tried to solve this problem that if you have very little information or some information, and in the overlapping plumes, then can you find out, is one source or two sources or three or four or five sources? That's not easy, but you have to do it iteratively and use some kriging and other thing and try to draw some boundaries or something, highlight some of where. So it is possible to make some guesses, but a simple answer is that if you have 5 sources and you assume 3, then there's obviously that's not even a decision variable. That there's no magic that that optimization model will know that there's another 2. Yes, no, that will not happen. But in that case, you should assume that maybe there are 5 or 7 or 8 possible sources. So that, yeah, we also sometimes do some preliminary analysis and then some kind of screening model and then do all these things. So that screening, that what I was talking about is that you do some screening model to find out how many number of sources are possible. It may not be exactly, but if you have 3, maybe 5 or 6. But if you have 20, even the solution becomes very erroneous. Your solution, your inference will not be correct. So many possibilities are there. Okay, so sometimes, but yeah, most of the times you'll get whether it's 1 or 2 or 3. So, but distributed sources another story. Mining site another story. But then the location of the sources most probably. You don't know the magnitudes. Okay. Any other? Okay then. Okay. This is the one I wanted to mention about ASA, because we are discussing ASA and in ASA. This Simon that is quite popular. That is simulated annealing code in Fortran by Bill Goffey. We call Goffey's codes Goofy's, and anyway what it is from NetLib. It handles bounds, constraints, everything it can handle. So that's very good. Also from Caltech, adaptive simulated annealing. That is what I was talking about. So this software will be able to estimate some of the parameters, and if you don't estimate these parameters, it's sometimes not very efficient. But if the software itself can estimate some of the optimization parameters, like in the adaptive simulated annealing, so it will be very, very useful. So this list is basically given in your notes if you want to have a look. Somewhere it will be there, and I think it shows lecture 11 or something, something probably arbitrary, but this one should be given. I mean, there are many, so like global minimum optimization, these different algorithms, and I don't know which one is better and worse. Sometimes for some problems one works better, some problems it does not work. So you have to try a bit. But as an algorithm, I think SA is quite efficient. Now this GA and NSGA that is developed by this Kanpur genetic algorithm laboratory. I don't think I'm not seeing this here, but anyway you can actually, or maybe it is I'm missing it. Yeah, you see, like it's genetic algorithm MATLAB. So MATLAB already has got. So this is GA is assumed. So most of the things are nowadays, at least from 1915 or 14, I'm finding that most of these algorithms are available in MATLAB. So if you have MATLAB access, that's very good. Now, one thing is that, and someone is asking me that, do you need, so generally we are talking about linked simulation optimization. Now, to solve a problem, of course, when you are using that, you have to have a calibrated model, or at least a simulation model, both flow and most of the times both flow and simulation and transport simulation model. So that is required because you link it. So that becomes slightly cumbersome. It needs effort. So this is not. I can give you a very small example, though I am giving you some examples. But there are some cases where you may not have a linked simulation optimization model, and that is in monitoring network design. Okay. And I will again discuss this some of the examples I think afterwards, monitoring network design. But here an example it might be that maybe it might not be very good formulation, but if I will say that maybe just a trivial formulation from ij for 1 to n or something like that, xij subject to maybe simulation summation xij is less than equal to p. Okay, this is very simple, and this probably doesn't work, but then I'll try to introduce the idea. Here what is that this might be very simple monitoring network design, may not make much of sense, but at least the idea I should understand. And that is, here what it says is that maximize the summation of this variable multiplied by Cij. So if you have some pollutancy, maybe you know the source, everything you know, but you at least can predict how the plume will be moving. So in that case, if you have, maybe you might have potential monitoring networks or monitoring locations, I should say. So maybe these and these and these and these and all everything. So I'll just for the timing consider only one time period. So if you know the sources, of course, so but you have some uncertainty, and some uncertainty maybe in terms because you don't know exactly what the parameter values are, but you know maybe with the mean value, maybe it is a heterogeneous area, but you only assume one average value. So there's lots of uncertainties. So you really don't know whether these plumes will be moving like this or these plumes will be moving like this, because even the heads might be slightly uncertain. It might actually move like this, and then if you are actually monitoring at this point and this point, it might not actually catch the plume. But if it's moving like this and you have some monitoring locations over here, you will not catch the plume. Okay. So how to so therefore the idea is to maybe you should be able to catch the plume and see where it is being polluted. And the yes. Yes. Yeah, but what I am trying to say is that yeah, if there is no uncertainty. Huh. Yeah, one is you can gauge the possible solution. I don't agree. So, and also if you have no uncertainty, you know exactly what the sources are. You know exactly what the pollution. This parameter values are, like K, porosity, anything, dispersion, everything. You know, very good calibrated model. Then you don't need a monitoring network. You know, so you should be able to predict. So why do you monitor this? So you don't need a monitoring network. You should be able to actually predict the values, and then that's it. But it's a question of when there is uncertainty, and if there is no uncertainty, there is no question of designing a monitoring network. And also it is a question of budgetary constraints, because unless you have budgetary constraints, so what's the point in, I can have 30 or 40 or 50 monitoring locations, and I don't have to design all these things. So. But I'm just giving you an example. Basically, it's an example on integer programming. Okay, that's why I'll go to the further. So what I can do is, so for different values of, maybe I can come up with different plumes, which is generated by randomizing some of the inputs. Okay, I randomize some of the inputs. And it might include Hij also, because you don't know exactly. It might be, so maybe the mean value of Hij at one location is equal to say 15 meters. Okay, but I can randomize it between some limits or something like that, which the values might lie between 13 and 10, or 13 and 16 or something like that. Okay. So in that case, for every different hydraulic head distribution, I might get different plume, set of plumes. So I'm not getting one single plume, but maybe this is possible, this is possible, this is possible, this is possible, this is possible. So that means we may get multiple realizations of the plume. Okay. And if I knew exactly this is the plume and not this one, then of course I don't need a monitoring network. So then that means I might actually say, okay, it might move like this. What is the best location? If it might look like this, it might move like this. So therefore, maybe just as a very crude objective function, I can say, let's maximize the product of the concentration at this location. Any location is ij, okay, and here the concentration Cij. And let us say this Cij is the simulated one, which may or may not be correct. Okay, simulated concentration at this point. So if that is the one, I will multiply the Cij by Xij and say that let us maximize the summation of the Cij into Xij. What it means, and that is what I want to discuss. What it means is that if Xij can be, so Xij can be equal to 0 or 1. Okay, it is 0 or 1 variable. So it can take a value of 0. That means if your concentration, I am doing maximization, is very high over here, it is very likely that you like to place a monitoring network at that point, or monitoring location will be at that point, because then you will increase the objective function value. So by making Xij equal to 1, you will actually increase the objective function. If you make this Xij 0, though Cij is very large, suppose that any is large at some point here or there, if you make Xij corresponding Xij equal to 0, of course you are reducing the objective function value. So if you have 3 different points to choose from this point to this point, this point, suppose Cij, this is Cij is equal to 15, maybe 17, and maybe 25. Okay, and you want to make sure that at least you choose one point out of this, so that maximize this. Obviously, you will choose this one, because if this is 25 multiplied by Xij, which is equal to 1.0 in this case, it will give you the maximum advantage in terms of objective function. If you choose 15, your contribution to the objective function will be only 15 into x1. Okay, in this case it is 25 into 1. So that way, because it is 0 1 decision variable, so therefore the role of the objective function and the optimization model is to choose the values of Xij as 0 and 1. 0 means you are not choosing at a potential location, 1 means you are choosing at a potential location. How does it help? Now if I put a constraint on number of monitoring locations, say p equal to 7 or something, I don't have budget for more than or drilling more than 7 wells, okay, or something like that. So I want to say, okay, I will only take 7. How do you choose? Though this may not be the best objective function, but I can say, okay, I will have this kind of uncertain plumes, simulated, and then I take at this point what will be the corresponding concentration, maybe another point what will be the concentration, and based on that I try to maximize this, subject to the condition the total Xij is less than or equal to p. That means only 7 Xij values can be 1, and the rest of them will be all 0. Okay, 0 1 variable. So 7 or 5, whatever it is, will be equal to 1 and rest equal to 0, because I put a limit on the number of wells that will be installed, okay, for monitoring. Now what will be the solution? Solution will be Xij at every possible location, this location, this location, this location, either equal to 0 or 1. Now it cannot choose more than 7 points, so you will choose those points where this quantity will be maximized, or this will contribute to the maximization of this quantity. That is very simple. Okay, so then it gives you a design, because it tells you which locations you have a monitoring location, a monitoring point as per the solution. But I can complicate this slightly. I can say that because there is some uncertainty, as I said, I can randomly change h, I can randomly change k or n or any other parameters, or the sources even, because sources you are estimating your sources is some 30 grams per second or something like that, some flux. Okay, actually it might vary between maybe 25 and 35, and you can randomly choose these sources. If you do that, and then h also changes, some of the parameters changes, so one plume might look like this, another plume might look like this, another plume might look like this, or another. So here I will not only choose one value which is coming as a concentration at this point, but I might choose the summation of the values which is coming from all the plumes which have been generated. Understand what I am saying? So I have generated maybe 20 possible plumes. So I will pick up those 20 values at that point, which is coming from 20 different realizations of the pollutant plume. How those 20 pollutant plumes are generated? Because I am changing randomly maybe the hydraulic head distribution, maybe the source concentrations or source fluxes, maybe some of the parameter values, which are all possible. because there is always some uncertainty, always some errors, and therefore this a particular plume, suppose you take this one and from a source, and this plume is equally likely maybe as another plume like this. Okay, that's possible. So you don't know which one. So suppose I want this, the potential monitoring location is here. Okay, so now I'll get one value for this particular plume, this one for this point. I got another value for this particular plume over here. Then I can sum it over all the plumes. Suppose the plume number is PL or something like equal to 1 to n. Then I sum it over Cij PL for different into Xij. Okay. You understand what I am trying to do? I am saying that I will not only consider one particular realization, but I will consider all possible realizations, and then multiply this one by not only one Cij, but all possible Cijs which are equally likely, and then try to minimize this function. Therefore, I have to make a summation between the number of plume equal to 1 to n for this plume. So let us take one plume. Okay, I have generated this plume, and these are two monitoring potential monitoring points. Okay, say M1 and M2. And that for this particular plume, this has got some value, maybe 10 milligrams per liter or something like this, and this may be 25 milligrams per liter. Then I change my source randomly, and maybe maybe a smaller, so it might look something like this also. And at the same time, maybe not only the source, but I might change the hydraulic head distribution Hij, because that is also uncertain. I can randomly generate some of these Hij values, and that gives me this plume. And for this, maybe it is for this case, it is almost 0 for this one, and of course what is 25 for this value, and as you can see, it is out of the boundary. For the second plume, it is equal to 0. Okay. For this one, maybe this 10 for this one, and maybe almost 10 or 11 for this one. So it is, depending on where it is. For the second plume, it is 11 milligrams per liter. So you have, similarly, you can have other plumes like this, which are equally likely, and what I call is realizations of the plume, which are equally likely and possible. And so therefore, I can go back to this and say, okay, so therefore I can minimize this quantity Cij into Xij. Xij is a decision variable which is 0, 1 decision variable. Xij, again Xij equal to 0 means no monitoring, okay, monitoring well at location Ij, whatever is Ij, this particular value, and Xij equal to 1 means you actually place a monitoring well at that position. So in that case, Xij is a 0, 1 variable, which is therefore what you need for solving this is an integer programming. Algorithm. Now, for linear programming, everything linear, you might have this. This is your, I don't know, I don't want to go too much into it. Maybe your feasible space is here, feasible space is here. It depends. Maybe these x and y, this gives the physical space. X and y is here, and these are the bounds or whatever. The constraint said that your solution has to lie in this area, within this. And your objective function is something like maybe 5y plus 3x or something. You want to maximize this. So maybe you can see that has got a slope like this, like this, like this. So at this point, that's the maximum value you get, and that is the solution. Okay, linear programming is very easy. So because I don't want to go too much into it, because I can actually, for linear programming is very, very easy, because I want to maximize this. That maximum value is equal to some constant, say k. Okay, and I don't know what is this constant. So what I can do, okay, I can have this value or this value, this value, this value. The maximum I can get is probably when this line moves over here, and it is at the end of this point. The feasible space is here. The feasible space is here. Anything outside this is infeasible. Anything inside is feasible. So this is your feasible space. And the objective function looks like this, like some function like 5x plus what is that? 5y or 5x plus 3y, maybe something like that. So, and then I can say that this is, I can move this way, this way, this way. This all. I don't know what is the value of k. I said how much maximum value of k I can get is here. Okay, but that is very nice if you have a all linear constraint, linear objective function, and this is called linear programming. There's lots of software for that, available nowadays, not a problem at all. And that is where the response matrix method comes. If you have the objective functions linear, your constraints are linear in terms of the response matrix, you can use linear programming. Okay, so there's many software available. If I say this x is a decision variable which is 0 and 1, this may not be a solution, because maybe this is x equal to 1 is there and 2 is here, so you cannot take this value. It either have to be x equal to 1 or x equal to 0. Okay, so it cannot be any value because it's not continuous. It can be one value at 1 or 0. So then it becomes slightly problematic, and then you need actually integer programming algorithm. So now I am trying to minimize this. What does it mean? Instead, at any point for one particular plume, the concentration is given by Cij and plume number, whatever is plume number is PL, Cij plume number. So for any particular point, I know this value. For another plume, randomly generated, I know this value. For another plume, I know this value. So I take a summation and multiply this by Xij, which is decision variable is 0 or 1, and then I put a constraint saying sigma ij has to be less than or equal to p. P is the maximum number permitted. Okay, due to some budget or some economics or something, you don't want to more than so many wells. Then what will be the solution? It will choose those values xi equal to 1 where it can maximize this objective function. So probably that is the location for many of the plumes, many of the generated plumes which are equally likely. Each of them might be equally likely because it's like realization. So where the summation of these concentrations is maximum or large, it will only choose those points, because by that way, by choosing those points and for that particular point choosing xij equal to 1, it actually increases the objective function. But if it chooses xij equal to 0, it will actually decrease the objective function. So there is scope for increasing the objective function by choosing xij equal to 1, but if you choose xij equal to 0, where Cij is very large, so probably you will not be able to improve the objective function. So you are losing that capacity, that possibility of increasing the objective function. Because you understand, if at one point Cij is equal to say 100, another point is Cij is equal to say 20. So if I choose Xij is at this point is equal to 1, so obviously I am adding 100 to the objective function. If I choose Xij is equal to 1 at this point, I am only adding 20 to the objective function, because actually, oh, just put minimize. Here it actually maximize. So sorry. So maximize this. So because you are maximizing this, so obviously you will choose this 100 rather than 20. And if you have number of plumes, probably that is how you choose. So you now is slightly complicated in the sense that it is not one plume you are considering, but you are considering all possible plumes, or at least a set of possible plumes. Based on that, you are designing the monitoring network design. Monitoring network. Okay. Is that okay? And there may be so many other things. I will discuss some of this. We can look at the maybe gradient information, this information, that information, but this is one of the simplest one. But this is what is integer programming, and very interesting formulations can be done, because 0, 1 actually you can convert a nonlinear function into a step function like this. All kinds of things are possible with this linear is integer programming, but I will not go into it. But and I think Dr. Dhar, Anirban, so I think one of his thesis we used for one of the monitoring network design problems, we used integer programming. Very interesting. I used to use a lot of this because the formulation is very interesting. Okay, so you might look at it, but then you will get this software for Lingo or Lindo. These are of course commercial softwares which can solve not only integer programming problems, which is mixed, means say x1, x2, x3 are 0, 1 variables, they are integer, and maybe some other variables y1, y2, y3, these are all continuous variable. Okay. Okay. So this y1, y2, y3 is continuous, so you will get this. So that's for mixed integer programming. That is much more useful. Only problem is that generally it's very easy to solve this mixed integer programming and other things when the objective function is linear. So linear MIP, mixed integer programming algorithms are quite easy to get and easy to solve. But if the objective function become linear, or some of the constraints become nonlinear, sorry, if become nonlinear objective function, or nonlinear constraints, with integer variables, then things becomes quite complicated. It is not easy to solve. The way the search is done is for 0, 1 it becomes difficult. Even GA will not work very well. So this is one thing. But I think as far as I remember, Simplex is one software where it has got nonlinear mixed integer programming, and also all kinds of things are available. Simplex, Lindo and Lingo is very easy to use. Even the accountants and others can use this for linear programming, and and also integer programming. So you can look at these two also, but they are commercial softwares. Simplex also you have to buy it, so it is not. But again, maybe MATLAB has some of this already. So this is very interesting. So you need some special kind of optimization algorithms when you are solving actually for say 0, 1 variables, which are like design of a monitoring network. Most of the times you actually have this mixed integer programming or integer programming formulation. But one good thing about this, so when you want to solve this problem, this monitoring network design problem, though it is a very simple one, I don't need to link it to this is one case where linking is not required, because all I need is the concentrations which I can actually generate or simulate outside, and the formulation needs the Cij values only, which I can actually import. I don't have to do it at the same time. I can solve it for different maybe randomly generated plumes. I can get the Cij values at different locations. I can use them, construct the objective function value over here, and then actually solve it. So I don't have to link it. This is the easiest thing. If you want to, I think if you want to do a master's thesis, and try for a monitoring network design, because you don't have to link it. You can solve the simulation model separately, use this, and then of course you can play with some of the objective functions and constraints and see. Okay, so that is what I'm saying that. So because linkage is not required in one case, generally some of my master students I encourage them to use this, because linking the simulation model, optimization model, and doing all these things takes time. Okay, so this one you can externally solve it and then input it in the objective function or in the constraints, solve it. Okay, so this is one thing I wanted to say. This is a different kind of program. Integer programming is very good for some kind of decision making, where 0, 1 or yes, no decisions are involved, and some Lingo, Lindo, and I think Simplex also has got very good software for this. You might be able to get something in the MATLAB. So these all about, and I will discuss some of this when I discuss some examples of the monitoring network design. Before I go to something else, maybe I'll go to multi-objective optimization. Let me see if I can find this. Oh, not this one. Let me see the other one. Maybe it's in the other one. So because there's a figure there, so it might be useful to present that figure. Thought it was here, but anyway. So let me just go see. Now, so long we are talking about only one objective function, say maximize f1 and maybe maximize f2. Sorry, f1, but we might also consider maximize f1 and maximize f2, or I can say maximize f1, which is one objective function, and minimize f2. So all these combinations are possible. So now, or even minimize say f3, 3 objective functions, 2 objective functions, 1 objective function. The moment you have more than one objective function, it becomes a vector optimization problem. Okay. So it becomes a vector optimization problem because you have more than one objective function as a vector. Now the definition of multi-objective is, I'm just trying to see if I have. Yes, so I would like to so that means you are now so long is only one objective function, now two. Now a multiple objective optimization model is actually multiple objective. What I am trying to say, that you might look like f1 is there, maximize f1, maximize f2, minimize f3, and you can say, okay, there is more than one objective function, and should I call it a multiple objective optimization? So that is the question, and this is very important to understand, that it is a multiple objective optimization if, say, the objective functions are actually conflicting. If they are conflicting, only then you will call it an I will tell you what it means. Suppose, and otherwise it is not. You might have three objective functions, then it is not conflicting. So then you can actually add them. Suppose you can take maximize f1, maximize f2, maximize f3 or something like this, just to make it simple. So you can actually, if not conflicting, then I can just add them, maximize f1 plus f2 plus f3, and it will give you this. There is no harm in doing that, because you want to maximize, they are not conflicting. You can combine them, add them, and optimize it. So it becomes a single objective. So it is not conflicting. What do you mean by conflicting objectives? And this sometimes people do not understand this. You have to prove they are conflicting. That means, suppose I have an objective maximize some f1, just like the example I was giving in the morning. Maximize maybe the beneficial pumping from an aquifer, and may minimize maybe barrier pumping from an aquifer. And generally what happens in a, maybe you have a, just an example, this is the sea, there is some, this is maybe salty water, sea water, and this may be the aquifer, and the interface between these all salty water, salt, and this may be fresh water. And then if you, and actually, okay, the ground surface might be something like this, maybe I should say, and this might be the water table is here. So if you go on pumping from the aquifer over here, this is the land surface, there is a sea over here. If you just start pumping from here, this water table might go down. If it goes down, what will happen? The sea water will start coming in this direction instead of the other direction. Previously maybe it was like this direction, but as the water table goes down from here to here to here, the more sea water will come into the aquifer to make it saline. Okay. So one of the ways we try to do it is to have barrier wells. Maybe this is the sea face or something, this is the sea in this side. So you want to pump over here for agriculture or maybe domestic use, all kinds of water use over here. but also you pump from here, because when you pump from the wells, so what happens? The cone of depression looks like this. So if you are pumping from here, so you along this line of wells, you will have a head like this. Head will be something like this. Okay, this is the well. Another one will be also similar. So what happens is that you have a gradient towards the land from this side, but also you have a gradient from the land towards the sea by barrier well pumping the other way, and therefore all this you are actually trying to minimize the saltwater intrusion by pumping more from this boundary or near the sea face wells, which are called barrier wells. You are creating a gradient which will actually minimize or prevent the salt water from entering, because near the well you have gradient which is like this and like this, and if the gradient on the other side of the well is this way, it is difficult for the salt water to enter this way because up gradient. Okay. So that is what it is sometimes, and a combination of these two will be very useful. So my objective function might be the maximize F1, which is beneficial pumping, or minimize the barrier pumping. If you have these two objective functions, then generally what will happen is this. So you are trying to maximize the beneficial pumping. Of course, you want to supply more water and make more profit, or more economic benefits, or you minimize the barrier pumping because you are just throwing away this water. It's very salty. You have to somehow dispose it, so you want to minimize as far as possible. But you want to do it together, because by increasing this, so you might have a situation where like this. It is probably that is not the way. This type of scenario, where it says that if you want to pump very small amount of water for beneficial use, that is F1, the corresponding barrier pumping required to maintain some salinity, which with me some limits. I have some limits on salinity. It should not exceed this value, that value, or something. So the barrier pumping necessary is very small over here. Okay. But if you want to increase the beneficial pumping, the barrier pumping is higher. If you want to maximize this pumping, the barrier pumping is higher. If you want to maximize this pumping, the barrier pumping is higher. Okay. So that means you want to maximize this the moment you want to, and you want to minimize this. So if you increase this, of course that is what you want. You also increase this, which is not what you want. You want to minimize this. You want to make it as small as possible. So if you make it bigger, it becomes bigger. What you want is to make it smaller. But if you want to increase this F1, as a result, you need to increase also this other, maybe F2 I will call it, the barrier pumping. That means you cannot achieve higher amount of beneficial pumping by not increasing the barrier pumping. So because your objective function was to minimize this, and also so you want to minimize as far as possible, and you want to maximize this as far as possible, but you have to sacrifice this one to increase this. So that means the sacrifice is necessary in the first objective function to increase this for this, or actually have to sacrifice in the second objective function this barrier pumping to make this first objective function better, or increase its value, because you want to maximize it. That's the question. That's why it is conflicting, because I will say that if you want to maximize it, but if you make it only 10, maybe the barrier pumping is 5, fine. But if you want to make it 15, barrier pumping required is maybe 9 or something. This 5 is increasing, but what you want is actually decrease it as far as possible. But increasing the maximum pumping for beneficial use, you have to actually increase the other way, and therefore this is a conflicting objective. Okay. This is a conflicting objective. Is that clear? Is that clear or not? So, because one objective is to maximize your pumping, which is for maybe water supply. Another objective is to minimize your pumping from the sea face wells or something, barrier wells. But you can only increase the pumping for beneficial use by also increasing the pumping from the barrier wells. So therefore that goes against your objective function of minimizing the pumping from the barrier wells, because you have to sacrifice that and actually increase the pumping and not decrease it to pump more from the inside the well. So therefore these two are actually conflicting objectives. If this is a conflicting objective, this is a multiple objective problem. So this becomes a multiple objective problems. And you can have more than one. You might have two, so it becomes surface. You might have three objects also. Those are possible, but each has to be actually conflicting with each other. Otherwise, it doesn't make sense. Okay, that you have to understand. Now, because it's a multiple objectives, so I call it a vector optimization problem. And if it's vector optimization, so there is no particular optimal solution. There is no particular optimal solution. I cannot say this. Only I have a trade-off between these two. So I have it maybe between F1, that is the beneficial pumping, for example, and barrier pumping, which I want to minimize. So this is like this. I want to. Okay. And it is F2. So what it says that if you increase this one, which you increase, also you have to increase. If you increase the F1 by this amount, so this is the amount. So increase the delta F1 is this much. The necessary increase in F2 is delta F2, which is given by this. So there is a trade-off. That means to increase F1 by this much, you have to also increase F2 by this much, which is a sacrifice because you are actually want to minimize. So there is a trade-off. Okay. And the trade-off might be different here, 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 and here. Might the trade-off is very much. So, even to increase the objective, the barrier pumping by a small amount, you might have to actually increase the barrier pumping by a lot over here. So, the trade-off is different. Here is maybe more flat, maybe it is more. So, here if you go, maybe to increase the beneficial pumping by a small amount, you have to actually increase the barrier pumping by a lot, this much. Okay. Over here, it is only this much, for even for a larger amount. So that is the trade-off, and that is the important information. Now this is called the Pareto front. For a multiple objective optimization problem, this Pareto it is also called Pareto front. Is called non-inferior solution front or solution front, and also called Pareto optimal solutions. So what it says is that if you get a solution over here, suppose I get this is the trade-off that's required. This is my Pareto optimal solution. Somehow I find this solution inside, and these are all possible. I have got some points, and from that I can construct this. Okay, as if you select by some means that a solution over here, well, this solution exists. That means for this level of barrier pumping, which you want to of course minimize, you can achieve this level of beneficial pumping from here to here. The level of beneficial pumping only this much. Okay, if you go from this one to this one, so actually from this front, which is a feasible solution, you should be able to achieve this much of beneficial pumping. But if you have a solution for somehow you got this solution that for the same level of barrier pumping you are getting only this much of beneficial pumping, that means your solution is not acceptable. You can do better, because you can keep the level of barrier pumping at the same level and then go to this level of beneficial pumping. So this is not a good solution, it is not acceptable solution. The maximum or best you can do is here, because this then represents the front where the best solution lies. So you can do as good as this. Of course you cannot, here is not feasible. You cannot have this much of barrier pumping and this much of beneficial pumping. That is not possible. This is the limit, this is the boundary, this is the envelope. But any solution you get inside this is inferior solution, because for the same level of barrier pumping, you can, if you get a solution over here, that means your beneficial pumping is only this much, but for the same level of barrier pumping you can go up to this of beneficial pumping. So this is a good solution, these are bad solutions, these are inferior solutions. Okay. So in multi-objective optimization, always you get a Pareto front, which is called the non-inferior front, and these solutions on this non-inferior or Pareto front is called non-dominated solutions. Okay. Very important. Now, as I said, is because it is a vector optimization problem, so it does not have an optimal solution really. So all it says is that if you want to increase at this point your beneficial pumping by this much, and then this much of, so this much of increase in barrier pumping is necessary. But maybe here if you go, maybe for this much of increase in beneficial pumping, you have to increase the barrier pumping by this much, which is much more. Okay. So as a decision maker, you should be able to make a decision whether you want to do this sacrifice of barrier pumping so much and then increase it by the only small amount, or you want to stop here or here or here. You cannot get a answer, direct answer, without, unless you have some other information, or what you call, and I just mentioned this, you have a utility function of your own. That means every point you know that what is good for you. Okay. Suppose you want to do something. Suppose you want to buy more cars and more houses. Okay. Okay. Or if you want to buy another more car, maybe, or another more house, you don't know what is the cost, and do you want to go. So maybe if you buy another more car, you cannot get one more house, so you have to decide whether you have to go for this or that. So that's the trade off. Okay. Now if I say you have to spend more, maybe some 5 lakhs for a car, or maybe 10 lakhs for a house, maybe you should say, okay, I'll go for a car first. Okay. Then you already have a car, then if you say, okay, now to buy another car, a better car, maybe you have to spend 15 lakhs for a car, and maybe you can still get a house for 10 lakhs. Then you'll say, okay, I'll go for the house because it's better for me. Okay. So trade off will determine that whether you want to stop here or you make further trade off. Okay. So for this, it's expected that you have a utility function. Utility function means you know that whether at this point you want to make this much of sacrifice, or this much of sacrifice, or this much of sacrifice, what is acceptable to you. So what it says is that if your barrier pumping is very, very small, or okay, I'll just add, is very, very small, so you don't mind sacrificing a bit and increasing your beneficial pumping. So this is very small. Again, it's very small, you can go and then increase your beneficial pumping. But here we are not ready to sacrifice this much of, only gain this much of beneficial pumping and increase the barrier pumping this much, which is unacceptable. So that trade off is unacceptable. Maybe somewhere over here you have your own utility function which says that at this level of barrier pumping I can sacrifice this much, at this level maybe at this level I can sacrifice slightly more or less, here less, and wherever this becomes actually tangential, your utility function is this one, which says that what is the trade off you are ready for. That means you want to make that trade off, you are ready, good for you, it's okay for you. But if you have to make a lot of sacrifice in one objective to get a small amount of increase in other objective function or improve, then probably not go for it. So then you should have an implicit utility function which is sometimes psychological, or you might not be able to explicitly express it, but you should know more, maybe I will not go any further. So the decision maker's preference ordering is necessary. So to get an optimal solution, you need the preference ordering by the decision makers. It may be the water managers, it might be some political people, or all kinds of things. Okay, how far do you make? Are you going to pump too much of this barrier water and throw away the water, this all saline water? It is creating some all kinds of environmental problems, or maybe and only as a consequence you are increasing your beneficial pumping by small amount. No, I stop it. But then I am only pumping very small amount of barrier pump, from the barrier wells. So why not increase that and maybe more, because your amount of beneficial pumping is also small. So I'll make that sacrifice and go. So from here to here is easy to go, from here to here is very difficult to go. But generally decision makers will have their own implicit preference ordering, which is called utility function, which says what is the sacrifice they are ready to make, and when that sacrifice matches with this one, this slope and that slope actually matches, that's probably the best solution. Things become more complicated if you have more than one decision makers. Each might have a different utility function, and then that goes to the realm of conflict resolution. I will not go into it. So maybe you bring them all together, take a vote or something, or do some sacrifice, ask them why they preferred it, why not, make some discussions, do some bargaining, so all kinds of things. Sometimes the politicians will also decide, so that is another story. Okay. but conflict resolution is the only way you have multiple decision makers and multiple objectives. Okay. So, and this is very, very interesting, and you can read this paper if you are very interested. Long ago, I don't know whether it is reference to this paper. No, I don't have a reference to the paper. I have taken it from there. This is actually one paper I wrote in 1986, which is long ago. I thought it was that time nobody, not many people have heard about multiple objectives also optimization, but I wanted to solve this problem for some aquifer management in Arkansas, in USS. We are working on that. I thought I called these people from the water resources department, and they had this problem of not their problem was that how much to use surface water and how much to use groundwater. Okay, and they are conflicting in some ways because surface water you have to pay a lot to maybe use it over there, and also there is some pumping cost and other things involved with the groundwater, and there is a trade off. Maybe if you are using this level of surface water, then this is the amount of groundwater. So if you want to use the mode of surface water, of course maybe the cost will increase. So there is some conflict, and that example is given. So exactly, so I forgot all the details, but then to get a compromise solution, I called some of these people together and then say, okay, now try to find a compromise solution, and then let's see what happens. So that one actually I got some solutions for this one particular solution. Okay, so that was a very good example. But at that time, 1986, I think it is very new. Not many people have also even used multiple objective function. But I used what is called the interactive graphic based. So you use this information and then try to. So this is the utility function of the decision makers, and this is the Pareto front over here. You can see when it's tangential, that's the best solution possible, slightly, and the trade-off is given by the delta Z2. Maybe that is the change in the required change in the objective function 2 for a given change in the objective function 1. That means change in Z2 for a given or specified change in Z1. So that is the trade-off. But the utility of function will tells you that for the decision makers will also have what is acceptable to them. So how much of maybe Z2 they are used ready to sacrifice or increase for another more unit of Z1. Okay, so that is, so when they coincide, that should be the best solution. But to get that answer is because nobody says that is my utility function, and this you have to extract it. Okay, from their psychology and all these things, and sometimes by let them fight it together. Okay, fight it out. Yes. Okay, for the Pareto front, as it is for from an optimization point of view, I should be able to. Okay, I did not go into that method because what happens when you have more than one objective you can solve. Okay, so you get the optimal solution. Fine, you are happy with it. Two objectives, what you do? One way of doing it, and I hope I have time. So it will be, and this is a constraint method. I'll So I have maximize Z1 and maximize suppose Z2. Okay, these are two objectives. This is conflicting. So if you increase one, you have to decrease the other one. Conflicting. And subject to all constraints, and whatever constraints, physical constraints, is whatever you have, you might have the link simulation model and other managerial constraints that pumping cannot be more than these from one well, these and all kinds of things are possible, subject to the constraints, usual constraints. Okay. Now, how do I get a solution? One way and very easy way, and I think this is quite useful, is I maximize Z1, and for that I find out what is the value of corresponding value of Z2. So that means I am not putting any constraint on Z2. Let's say maximize Z1 and see. So I am not, and let's see how much value of Z2 it can get. Okay. Okay. Or other way, if I look at it, I am not putting any constraint on Z2. So that will give you the maximum possible value of Z1 it can get. Means I am saying I am just altogether removing this. If I remove this together, forget about this one. I say let us solve it as a one single objective problem. So it should be able to get a maximum value of Z1 because the other objective is not coming into picture. So that's probably the best possible value we are getting. Okay, then I'll also say solve for maximize Z2 and forget about Z1 subject to all the constraints, same problem, but I am now forgetting about Z1. So, once I am forgetting about Z2, I am forgetting about Z1. So, that will give you the also maximum or the best possible value of Z2 you can get. Okay, that is the best value, because I am not considering the other constraints. So, trade off is not coming into picture. Now, what I do, I said okay, if there is no constraint, nothing else, other objective function is not hampering this solution. So, that is maybe Z2 is equal to just say 500. Okay. And when you use only maximum Z1, maybe this is maybe 3000 or something, some other things. I will just put some numbers. Okay. So, these are 500, that is the best you can get, the best you can get. Now, what I do is I will maximize Z1 subject to the same constraints similar, but I put such Z2 is equal to maybe greater than 0. Maybe it can, that means I am saying that best possible value of Z2 that is possible without any is 500, but I suppose put it as 50, or Z2 is greater than equal to 50. If it does not matter if it is equal to or greater than equal to 50, that it should not be less than equal to 50. So, then I am solving for Z1. Okay. So, what happens is that I am maximizing just like this one, maximizing Z1, okay, and maximizing Z2. So, first I get one value where I do not consider even Z1 or Z2, I get the maximum value Z1 is somewhere over here, or let us say yes, maximum Z1 is here or something, anywhere, it may be somewhere over here, and I get somewhere over here, and when I forget about Z1, I maximize, I get somewhere over here. Okay. So, this somewhere, it will lie somewhere over here and somewhere over here, that is the best thing to do. So, I will get these two values. Okay. Now, I am saying that let Z2 be greater than equal. So, in this case, to get this value of Z1, I am assuming Z2 equal to 0. Okay. Basically, I am assuming Z2 equal to 0, because that is not coming to picture. So, that is the best value of Z1 you can get, that means it is Z2 equal to 0. Now, I am saying not 0, but let it be greater than equal to 50. The moment Z2 is greater than equal to 50, probably, so you will not get this much, maybe you will get this much. Okay. You get this solution. Then maybe next time I solve with Z2 greater than equal to 100. Okay. So, now I am saying Z2 has to be Z2 at least has to be 100. So, here, and probably the value of Z1 you will get over here, and then again maybe I can put 125, 120 or anyway. So, I can get another value over here. So, I get a surface like this. So, I am optimizing by introducing the other objective function as a new constraint, which is saying that is the minimum level I want it to be satisfied, and for that level of satisfaction, what is the best value of the other objective function. So, that is non dominated, because that is the best solution that is possible. Okay. So, if you are taking out data, not really data, but I find this constraint method, this is called the constraint method. I find, though it is very crude and but I find it very good, because some other methods will not be, sometimes does not come up with this area, maybe this only this area. Okay. It does not compute or calculate whole Pareto optimal front, maybe only part of it. There is something called goal programming. I do not know whether some of you goal programming, which sometimes the problem is that what you do, you put some weightage on the first. So, you try to solve, maybe maximize W1 into Z1 plus W2 into Z2. Okay. So, W1 is some constant, maybe constant between 0 and 1, you can vary, and W2 also between 0 and 1 you can vary. Generally, that W1 plus W2 equal to 1.0, and that way for different values W1, W2 you might get some values over here, Pareto optimal front, but it might not actually produce this entire Pareto optimal solution, but this one is very, though it is crude, but it is very efficient in computing the whole Pareto optimal front. Okay. Sometimes, of course, there are other problems also. You might have, your front might look like this and like this. So, this is not Pareto optimal, this is not Pareto optimal, because you have better solution for this level of this, you can get this much of Z1. So, these are not Pareto optimal. So, you have to eliminate this, so only this part will be Pareto optimal. Okay. So, be careful about that, and goal programming might not even come up with this thing, the whole area. Okay. But if you can control properly, so once I am trying to find out what is the best value of Z1 I can achieve and what is the best value of Z2 I can achieve, and then I am forcing one of them to be satisfied at the minimum level, not 0, but then I am saying okay, then what happens to the other objective function. Then it will come up with the whole Pareto front. So that way, you know, don't need really that much of data, but it is a repeated solution. I don't know why this one. Actually,